All right, welcome to part 2, video 2 of our lecture for Friday, April 21st. We're again practicing how to calculate heat using our Q equals mc delta T equation. So let's look at kind of a more fun example than just thinking about heating water. So I have a 1.57 kilogram sample of pozole, which is cooled from 95 degrees, 95.2 degrees Celsius to 47.8 degrees Celsius. So you've got some soup, it's too hot, and you let it cool. If the specific heat of pozole is 2.960 joules per gram degree centigrade, then let's answer these following questions. So the first question, also feel free to roast me for my pronunciation of pozole. Sign of Q. What is the sign of heat? So let's think about going on in like a purely conceptual, non-mathematical sense in terms of our soup cooling. So our pozole is cooling, right? We know this because, one, I told you, right? It says cooling right here in the actual problem. But you can also prove this to yourself by looking at how the final and initial temperatures compare. So we see that the final temperature is less than the initial temperature. So that means that we started out with a large amount of thermal energy and then we wound up with less thermal energy in our soup. And let's think about what the sign of Q needs to be in a cooling process. So in a cooling process, we've got thermal energy that is transferred out of the system. And anytime we have this outward, away from the system, language or concept, then that means that we are looking at a negative sign for our heat. All right, let's prove if that's right. Let's actually use our Q equals mc delta T equation to determine in B here the actual value of heat. So what is Q? So the value of Q, we're going to write out our Q equation. So Q is equal to mc, which is our specific heat capacity, delta T. So our mass, let's look for that in our problem. Right up front, a 1.57 kilogram sample of our pozole is given. Okay, C, our specific heat capacity, C sub S, is also given as 2.960 joules per gram degree centigrade. And then delta T, which is final minus initial temperature. So I need to figure out what that is based on my starting and my ending temperatures. Again, remember here we have a final temperature that is lower than my initial temperature. So my final temperature was 47.8 degrees Celsius. And my initial temperature was 95.2 degrees Celsius. So doing that difference, 47.8 minus 95.2 gives us a negative 47.4 degrees Celsius. And now we can plug all of this in, being aware of our units. So let's just check that all of our units are good. Or they'll cancel is what I mean when I say they're good. Okay, so let's see here. I have a specific heat capacity that of course gives me the joule unit for my heat, which makes sense because heat is the amount of energy, specifically thermal energy, that's transferred into or out of a system. And energy is always in joules. Let's see here for my temperature. I do indeed have a degree C, which works out. That will cancel with my specific heat capacity. However, notice kilograms and grams will not cancel. So I need to convert to grams. Now you can do our regular kind of full conversion process where you've got the 1.57 kilograms and you know that in 1 big kilogram there are 1,000 baby grams, totally fine. Or, since you're a chemist and you're cheap and lazy, you know that kilo means 1,000 times larger. So I can say that this is 1.57 times 10 to the 3, which is 1,000. So I've made this 1,000 times larger. Grams. And now I can plug all of this information into my equation for heat. So Q is equal to 1.57 times 10 to the 3 grams times C, which is 2.960 joules per gram degree centigrade, times delta T, negative 47.4 degrees C. So let's just check that our units do indeed work out here. So grams per gram will cancel. So grams per gram will cancel. I've got now, looking for my orange, degree C and per degree C will cancel, leaving behind my joules, which is what we want. All right, so let's go ahead and do this. So 1.5 times 10 to the 3 is 1,570 grams times my 2.960 joule per gram degree Celsius times my negative 47.4 degrees Celsius. Okay, thinking about sig figs. Remember, anything that is given as a known constant does not have any uncertainty, so we do not include that in our significant figure analysis. So I'm left between the mass, which had 3, and my temperature, which had 3, so my product, my result here is also going to have 3 significant figures. So giving the full value, this is 220,277.28 joules, and it is negative. We have a couple of options here. We can express this either in joules to 3 sig figs, so that would be 2.20 times 10 to the negative 1, 2, 3, 4, 5. No, sorry. Negative 2.20 times 10 to the 5 joules. Or if we want to, we could express this in terms of kilojoules. And in fact, the kilojoule is a energy unit that we will see a lot popping up in chemistry. So I'm totally okay if you express your answers in kilojoules, since we'll be needing to do that anyway. So if I'm going to do kilojoules, I need to move my decimal over 3 places. 220 kilojoules. Both of these are totally fine. Calculations of my heat. So we hacked out the math, we plugged in the numbers, and let's make sure that this makes sense with what we predict from A. So we said that since this is a cooling system, thermal energy is being transferred out of the system and into the surroundings, and anything that's moving out of the system by convention has this negative sign. Do we have a negative sign in our calculated heat? Yes, we do. So we are happy. We have done this problem correctly. All right. So we have practiced calculating heat We are now going to look at finding the change in internal energy of a system based on its heat and its work. And then we will discuss enthalpy, and then we'll start on Monday with an example of heat transfer. We'll talk a little bit about enthalpy and its difference from heat. And then we'll continue with conversations about enthalpy.